Okay, thank you all for being here this morning. I am pleased to introduce Holger Dullin as our first speaker of the day.
Yes, thank you very much. Good morning, everybody. And thank you, first of all, to the organizers and specifically to Louis, there he is, for putting this beautiful conference together, bringing us to this nice place again. Of course, this is in honor of James, and I would like to briefly mention my connection to James. So when I got my first academic position in the UK, I didn't know many people in the UK, and I was not part of Maisie. I don't know, I came late to the party, basically. But Maisie existed, and you know that how many people are in this room that participate in that. And so I joined the group as a kind of latecomer, and it was the best thing that I ever did, I think. I learned a lot, and I met so many people that are important for my career and that I like and have fun with. And so thank you, James, for that. That was a great thing that you organized. That was very important for me. So I want to talk about the Kepler problem, and I hope I can tell you something about the Kepler problem that you don't know yet. So this will be a talk, I guess, that has maybe less geometric mechanics and more integrable systems, but of course the two are very much related, and I will explain a little bit about the theory of classification of integrable systems and how it relates to this problem. But let me just start by reminding you of the Kepler problem. We need to look at the spatial problem, otherwise this whole thing doesn't work. And so R and P are vectors in R3, and the equations of motions are simply this. This is the Kepler problem. R dot is P, P dot is R. And this is a system that is Liouville integrable. That means it has three integrals in involution. And the integrals are the Hamiltonian, which is kinetic plus potential energy. And then there is angular momentum, which is the cross product of R and P. And that's easy to see. You should compute this in your head now, that L dot is R dot cross P plus R cross P dot. And because R dot is P and P dot is proportional to R, this is 0, right? So L, each component of L is a constant. So I said there are three integrals of motion. In fact, there seem to be four, and there are four. There are even more, but let's take h and the length of L squared and the z component of L. These are three integrals in involution, and that makes the system Liouville integrable. So just briefly to recall, what I need from integrable systems is basically just the definition. I mean, okay, so we have symplectic manifold. I'm working in local and global coordinates here. The standard Poisson bracket. And this is an integrable system. That means I have a map from the manifold to Rn, where n is the number of degrees of freedom. And each component of this F has vanishing Poisson bracket with every other component, right? So Fi with Fj, Poisson bracket is 0. And not only that, these Fs must be independent almost everywhere. So that's the definition of Liouville integrable. I just wanted to remind you, because later I will talk about superintegrable systems and the relation between superintegrable systems and Liouville integrable systems. So it's important to have this in your head. So then the most important theorem is the Liouville-Arnold theorem, which says that if you have a regular value of this F, then look at the preimage of this regular value and pick out a connected component of that preimage. And if that is compact, then it's an n-dimensional torus. And I mean, so in the simplest case, maybe there is only everything is compact and there's only one connected component, then it's just saying preimage of a regular value is a torus. Right? And not only that, near this torus, in the neighborhood of that torus, you can introduce these special canonical variables called action angle variables, so that half of the variables are constant and the other half parameterize the torus. Okay, so let's go back to the Kepler problem. And in fact, this problem already has 4 integrals, as I mentioned, not only the 3 commuting integrals. Commuting means vanishing Poisson bracket. So the L, these 3 components of L are constants of motion, but they do not commute, right? So this is why I didn't use them in the definition of Liouville integrable, because I can't, they have to commute. In fact, there are even more integrals, right? In the Kepler problem, of course, very well known, there's Laplace wrong length vector, which is the cross product of P with L, and then minus R on R. And geometrically, what this means is just that every orbit is an ellipse in configuration space, and if you look at the vector that points to the furthest or closest point, I guess, of that ellipse, then that's the Laplace wrong length vector. So it tells you about the orientation in space of the ellipse. So now, how many integrals do we have? 1, 3, and 3 more, 7. So that's too many. Because we are only in 6 dimensions, and you can't have 7 integrals in 6 dimensions. So they are not independent. Right? But in fact, 5 of them are independent, and that's as many as you can have. And what it means is that every orbit is periodic. So why? Well, you're fixing 5 functions in 6-dimensional space, and if you know that the common intersection of these 5 hypersurfaces is compact, well, then it's a circle. In fact, well, topologically, and in fact, here these are ellipses. So, yeah.
It's not only when energy is negative?
Yes, that's right. So when I said if it's compact, in fact, when the energy is negative, then they are compact. They would still be one-dimensional if the energy is positive, but of course, then they are not circles. Yeah, thanks. Okay, so very special, very important, and there are a couple other systems. If I have time, I'll mention them in the end. The isotropic harmonic oscillator, the free particle, and geodesic flows on spheres all are in this very special category that they are sometimes called maximally superintegrable. That means they have so dimension of phase space minus 1, that's the number of integrals that you have. Okay. So I will switch back and forth between the classical and the quantum description. So just very briefly, how do you get the hydrogen atom from this? Well, basically you replace p squared by the Laplacian with a minus sign. Right? So that's the standard kind of canonical quantization. So this is the Schrödinger operator, and in the quantum case, you're interested in solving the stationary Schrödinger equation. So apply this operator to a wave function. This is a function on R3, and require that you have an eigenfunction. Right? So then this E is the energy, and they are classically known. Well, they're negative for this compact case, 1 over 2n squared, where n is an integer, positive integer. I will tell you a little bit more about this as we go along, but to point out the most important thing for me at this point, or for the whole talk, is that this eigenvalue of this operator is highly degenerate. So when this integer n gets larger, then the degeneracy of that eigenspace, with that eigenvalue, is n squared. And in some sense, I guess what I will do is take this large eigenspace of dimension n squared and choose a non-standard basis in that space. Of course, you have a choice for the spaces in that space, and my whole talk, in some sense, is about choosing a natural but non-standard basis in that eigenspace. Okay, so a little bit more about superintegrable systems. So I already explained this, maximally superintegrable. And so there is if you want an improvement of Liouville-Arnold for this situation. Liouville-Arnold says if you have Liouville integrable system, that means you have n commuting constants of motion, then you have action variables. If you are in the situation where you have more integrals, then Nikoroshev says there are special variables, I, phi, those are actions and angles. But then there are more, p and q, some symplectic coordinates. And the strange thing about these p's and q's is that their dynamics under the Hamiltonian is they don't have dynamics. They're all constant. So p's and q's are constant, and I and phi are as before. So I is constant and phi is an angle. The main difference here is now that because you have p's and q's, you don't need half the dimension of phase space i's, but you could have less. And in the extreme case, you have only a single I, even when you're in n dimensions, in n degrees of freedom. Then you have a single action, a single angle, and lots of variables that are constant. Right? So that's the Nikoroshev variables for superintegral systems.
How many p's and q's?
Well, that depends. So I guess in the maximal superintegral case, you have a single I, a single phi, and so therefore, well, if your dimension of phase space is n minus 2 p's and q's. But so another way to think of this is that you have, if you let the dynamics run with a generic initial condition, then the orbit will trace out a torus, let's say irrational rotation number, but the dimension of that torus is not half the dimension of phase space, but it is smaller. And so that's why you need fewer i's and phi's. Okay. So since we are in this maximal superintegrable case, the flow of H defines an S1 symmetry. Right? So that's the other important trivial observation, I guess. We have a natural S1 symmetry. And well, and if you have a symmetry, then you should do a reduction, and that's the reduction that I will do. I will quotient the Kepler problem by the flow of H. And the way to do that is, well, one way to do that is to use the invariance of H. So use all the constants of motion in some sense and try to find a version of them so that their Poisson bracket closes, and then this is a nice Poisson reduction. The strange thing, of course, is that if you quotient by the flow of H, there's no dynamics anymore, right? Because you quotient by the dynamics.
Does the difference of periods make a problem?
Yes, it's correct. So if you want to quotient, I mean, S1 symmetry means you should have constant period, right? And H does not have constant period, but in fact, the action, the n, right, or the I guess, in Nikoroshev theorem, that is a function of H, and that has constant period, so you can quotient by that flow. Yeah, but that's right. So technically, I would quotient by the flow of I, not the flow of H. Okay, but there's no dynamics left, just geometry. And the geometry, as I will explain, is that you end up in a space that is S2 cross S2, which is the coadjoint orbit of SO4, because this symmetry that we're quotienting by is SO4, in fact. So because there are, well, it's maximally superintegral, so we have not only SO3, which is the symmetry that leads to the angular momentum, we have, in fact, a larger symmetry group. And that's the reduction we need to do. Okay, so fix H, and that means also fix n, this action variable, and then quotient by the flow of n. And it is natural to scale this E, the Laplace-Runge length vector, with the value of this n, or square root of minus 2 times the energy, that is. That is another vector now, k. Of course, it's still an invariant of H, because n is an invariant of H and E is an invariant of H, so this is another invariant of H. You have lots of choices, of course, for finding invariants of H if you have so many functions. And the nice thing of using k is that L and k now together have a very nice Poisson bracket, and that is, in fact, the Poisson bracket of SO4. Right? So Li, Lj, Poisson bracket is Lk, etc. Right? So this is the SO4 algebra. And the most important thing from the point of view of reduction, I mean, is also the observation that this Poisson bracket closes. I mean, so any Poisson bracket between these 6 functions can be expressed in terms of the 6 functions. Right? So SO4 algebra if you look at the Poisson structure matrix that has this, I mean, this is a Lie Poisson structure, of course. It has two Casimirs, and the two Casimirs I want to write as this. Again, there's choices of how you write the Casimirs, but I like k plus L length squared is constant. In fact, that's n squared. And k minus L length of that vector is also constant and is the same as the other one, right? So these are k and L are vectors in R3, and so each of these equations now you can think of as defining a two-dimensional sphere, right? So it's two-dimensional spheres, right? This is one S2, and this is another S2. And that's how you can see that this reduction brings us to S2 cross S2. And from a general theoretical perspective, I guess you would just say the coadjoint orbit of SO4 is S2 cross S2, right? But this is the down-to-earth way of computing it, if you want. And yeah, coming back to Nekhorozhev's P's and Q's, so Nekhorozhev was a local statement. So he says he can choose these coordinates I and phi. So I is the n, phi would be the angle along the Kepler ellipsis, and the p and the q would be local coordinates on this S2 cross S2. But now we get something slightly better, which is the global version of this statement. Okay, so that's the reduction by the flow of H. And as I said, since we reduce by the flow of H, at this point, there's no dynamics on this S2 cross S2.
So, just to understand, so if you added an extra term and did averaging, you could push it down to the set.
Extra term where?
To the Hamiltonian, when people do secular variables and special mechanics.
Yes, I mean, so one other natural way to get this is, yes, if you do kind of perturbation theory, is that what you're thinking? Yeah, and then you would average over the flow, basically, of the system, and you would end up also on S2 cross S2, but then you would have dynamics on S2 cross S2, which comes from that additional term that you average. And this is, of course, well, Boris is one, and his collaborators have done this a long time ago, and so this is well known. The strange thing, I guess, that we're doing is we're doing this without the additional term, right? So which we can, right? But that's why we end up without dynamics here at this point.
This can be understood as the moduli space of solution, or some space of solution.
Yes, that's the other interpretation. Yeah, exactly. So if you do this quotient, then the S2 cross S2 classifies all the Kepler ellipses in space, right? And so you can say all these Kepler ellipses are S2 cross S2. Each point in S2 cross S2 corresponds exactly to one ellipse. Okay, so what's the relation between super and Liouville integrable now? Yeah.
Why are the two Casimirs equal in value?
Yeah, no, it is also special in some sense. If you look at the spin systems that Boris discussed yesterday, then you would have a similar, well, you would have something on S2 cross S2, but they would have different radii. But in this case, that's how it comes out. They have the same radius. But yeah, that's not the general case.
That seems to be a restriction on what possible values k and L can take. And I didn't think that in fact it was quite such a restriction.
Yeah, I don't know. I never thought about it this way. Maybe, I mean, the scaling is important in that connection, but yeah.
If you used E instead, you would always get more.
Yeah, so I mean, it's true. I mean, it is some kind of accident, if you want, that they have the same radius, but they do have the same radius. Okay, so Liouville integral means n independent commuting integrals. And if you have a system that is super integrable, or sometimes that's also called non-commutatively integrable, that terminology goes back to Mishenko and Fomenko, and they conjectured that if you have a system that is non-commutatively integrable, that it is also Liouville integrable. So at first that seems almost like a strange question, right? Because you say, well, if you have too many integrals, right, why wouldn't you have enough? Then you certainly have n over 2 integrals. But the point is that they have to commute, right? So it's not obvious that from your many non-commuting integrals you can build the right number of commuting integrals. And this was only proved in 2003 by Sadetov and then improved a little by Boltsinov, that this is actually, this conjecture is true. And what is still kind of a little open problem in this relation is that it's not in the same functional class. So here we start with very nice integrals, polynomial integrals. Right? So then you would hope that your Liouville integrable system also has polynomial integrals, but that's not true in general. In our case, that is obviously true, but in general, this is not known. Right? Anyway, so the key point of what I'm going to do is this observation that a superintegrable system may be Liouville integrable in non-equivalent ways. Right? So there is, even though I guess, well, it was a conjecture that it's Liouville integrable at all, but now I'm saying, well, but maybe it's Liouville integrable in 2 or 3 or infinitely many different ways. Right? And that is, in fact, the case for the Kepler problem, at least. This can be made Liouville integrable in non-equivalent ways. And I want to talk about one of these ways in particular. Okay, so let me define a bit more precisely what I mean by that. So given a superintegrable Hamiltonian, like the Kepler problem, and I want to say Liouville integrable realization of this H is a collection of functions that includes H and then n minus 1 more that are in involution and independent almost everywhere. Right? So that's a natural definition. Right? It says you need to include your H so that you're talking about the same system, but all these other functions here, they are somehow at your disposal. Right? And so the question is now, in how many ways can you build this? Right? How many realizations, Liouville integrable realizations are there? Right? So for Kepler, so we already saw that when we quotient by the flow of H or the action, then we get an integrable, well, we get a system on S2 cross S2, which doesn't have dynamics. Right? So now I can say I'm just looking for 2 functions. Yes?
What would be the symplectic form there?
On S2 cross S2?
There?
Yeah, it's the standard. I mean, each S2 has a standard symplectic form. Right?
With same weight?
Yeah, so that's the question of the radius again, right? Since they have the same radius, yes, it's the same weight. Yeah. Well, I want to say there are infinitely many such realizations for Kepler. Why? Because there are infinitely many integrable systems on S2 cross S2. So each such integrable system on S2 cross S2 will have some integrals. Call them F2 and F3.
You say no dynamics, so what it's
Sorry?
foliation to tori, what do you mean by integrable system now?
Yes, I mean Liouville integral system on S2 cross S2. Right? So after this reduction, I'm asking for a Liouville integrable system. And I'm saying there
There's no dynamics, so
there is no dynamics, but I'm just looking for integrable systems. Right? So I need to find, yeah, exactly, foliation into tori. So I need to find these 2 functions. Right? And since I know that there are infinitely many systems, integrable systems on S2 cross S2, I mean, because you can write down infinitely many, or you can write down one that has a function in it, there are infinitely many realizations. So that's kind of now says, oh, well, maybe it's a silly question. So somehow there are too many realizations, right? Infinitely many is kind of boring. So I want to now make it a bit harder and look at, with good reason, a particular one. And I'll explain why that particular one is a good one. Okay, so here's the standard realization of the Kepler problem that I started with, H L squared LZ. And the one that I want to look at now is H G LZ. So G is the new constant of motion, and that's L squared plus 2a and the Z component of Runge length. So this is a deformation of the original one. When a is 0, we get back here. And in general, this is an independent function. So this is a different integral, defines a different integrable system on S2 cross S2. And of course, you can make these statements for Laplace Runge lengths in the quantum case. So in the classical setting, it seems kind of silly to do that. And your questions already say that, right? That, well, I don't know. This is kind of, there is no dynamics. So why do you define an integrable system? So let me explain why I think this is still a good idea. So classically, of course, what one should do is use the geometry of super-integrable systems, which has a nice geometric description, and somehow one shouldn't butcher the system and force it to be Liouville integrable if it's not to begin with, right? So, but I think in the quantum case, the situation is slightly different because each realization, each Liouville integral realization, gives you a set of commuting observables. Right? So it means it gives you observables that, in principle, you can measure simultaneously, right? And that's a good thing, right? So, and that's why I'm saying, well, let's maybe select from these infinitely many integrable systems on S2 cross S2 some that are physically useful, maybe, or sensible, right? And they give us information about the hydrogen atom, and that's why this is a useful thing to do, right? So to be explicit, so you can measure H, L squared, and LZ simultaneously in the quantum setting. You can measure H, G, and LZ simultaneously, but you can measure all four of them simultaneously because they don't commute. But when you do this, when you measure these three, in some sense you learn something different about your system than when you measure these three, right? Because it gives you different information. So that's why I think it is a useful thing to do, right? And the choice of G, as I will explain later, is related to separation of variables, and so somehow it means that this G gives a nice quantum operator. And if I start with a kind of random system on S2 cross S2 that is integrable, it wouldn't give me a nice operator, and that's the restriction I want to impose. Okay, so let me talk a little bit more now about this particular new integrable system. So the energy momentum map, or momentum map of the system is G and LZ. And these are now viewed as this is a function on S2 cross S2, or a mapping from S2 cross S2 into R2. And the Liouville-Arnold theorem says that if you are at a regular value of this map, then the preimage is a torus. In this case, it's actually exactly a single torus. And if you are at a critical value of this map, then you get something else, and that's what this picture is about. So this picture is the image of S2 cross S2 under this map, F. And remember, F is just L squared plus the Z component of Vz times A. So here A is this value. N is fixed, right, because we quotient it by the flow of H, or the flow of N. And so the image of this compact symplectic manifold under this map F is some compact region. That's this region. And now let me talk about these red dots. Those are the non-regular values. Right? So on the boundary here, on each boundary, the preimage is a periodic orbit. And then at these corners, you get elliptic equilibria. And in the middle, you get what is called a pinch torus. So this is also an equilibrium point, but it has a separatrix which has the shape of a pinch torus. Again, you have to keep in mind that in some sense there is no dynamics anymore. When I say periodic orbit, of course, that this is a periodic orbit, well, not for the flow of H, right? Because the flow of H is gone. It's a periodic orbit in the sense that there is this integrable system defined by these two functions, G and LZ. And their common level set can be a one torus, and that's what I call periodic orbit, maybe confusingly. Right?
If I look at circular Kepler, just the circular, are they special points in there?
So what happens, and I will show this now in the next picture, is that so here, every point here, in some sense, if you would look in the original system, is a Kepler ellipse. Right? If you have a T1 here, it means it's a one parameter, a circle family of Kepler ellipses. Right? If you have a T2 here, that's a two torus family of Kepler ellipses. And the one that I'm most interested in is this one. This is this pinch torus. So this is a upstairs in the original system. This is, again, a two-dimensional family of Kepler ellipses. And they are glued together in this special way that they make this pinch torus. Right? I mean, or not glued, they're selected so that when you take their union, then they give a pinch torus.
But are they exactly circular orbits the boundary?
No, so this is, that's not related, but let me show you in this picture. So this is this pinch torus, and here you see lots of Kepler ellipses, and those are the Kepler ellipses that are selected in order to form that that torus, right? And you can see that there is a circular orbit inside, there's collision orbits inside. So basically it's a strange selection of Kepler ellipses that if you glue them together, well, not only that one, but all of them, then you get this integrable system. Right? So that's why I said it's a butchering of a Liouville integrable system, right? Because, or backward, butchering of the superintegrable system. You take these periodic orbits of your system and you force it into tori. And the way that you force it, well, that's determined by your function f, and the way that I want to do it is with this particular f. Okay, so I want to come to the main statement, I guess, which is that these are non-equivalent integrable systems, and the way that I want to show that is by saying that one of these systems has monodromy, Hamiltonian monodromy, and the quantum system has quantum monodromy. So let me explain what I mean by that. So let's look at a closed loop of regular values in the image of the map F, and every point here in the pre-image, not the pre-image in the six-dimensional system, just in the four-dimensional system, has a 2 torus. So that is a torus bundle over S1. And if this loop is contractible, let's say it would be sitting somewhere here, then because it is contractible, this is a trivial bundle. And the interesting thing is that if the loop is not contractible in the set of regular values, so in the set of white points here, there is this red point inside that's not a regular value, so this loop is not contractible in the set of regular values. And therefore, it may happen that the torus bundle that is defined when you take all these tori over this loop, that this is a non-trivial bundle. And if that's non-trivial, then we call that monodromy. And the obstruction in this bundle, I guess, it would be you cut it open and then you will get a gluing of the first torus to the last torus. This must be a map of the torus to itself. So it's some element of SL2Z, and that matrix will tell you what the monodromy is. So SL2Z in general, turns out that in this case, it can basically just be, well, it is in this case 1, 1, 0, 1. So one of the simplest cases. Okay, so one way to see this monodromy is by visualizing the actions. And what I mean by that is, so remember the Liouville-Arnold theorem gives us actions. One of the actions is LZ. LZ is an action by itself. So that's plotted here, there's nothing to do. But the other action is not plotted here, but this is the value of our constant g. But for each value of g, I could compute what that action is. And what I do here is basically I plot dots in equidistant fashion according to what the value of that action is. So I kind of, at this point, artificially introduce some kind of lattice by just saying plot the value, make a dot here for some value of the action, and then make the next dot a certain distance in action away, not in value of g. That's what this picture is, right? So you can kind of see the landscape of the actions over this image. And, well, this is locally a lattice, which, well, I guess follows just from the construction. I guess by action starts up here, and then if you do that, so I'm stepping in the same distance in the value of the other action. And so locally, this is a lattice, and the statement now is that this is globally not a lattice. So pick a lattice basis cell and move it around in the lattice. So first move it to the left, move it down, now move it to the right, and then back up to where you came from. And the statement is that under this parallel transport of a basis in this lattice, the basis of the lattice does not return to itself. Right? And here you can read off this monodromy matrix as a transformation from this cell to that cell. So this happens because there is this critical value inside. That's the focus critical value. So this changes when you change this value a. So when you send a to 0, you get back to the standard case. And when you send A to infinity, you get back to some other interesting special case in which the image of the momentum map turns into a polygon. In that case, there's no monogamy anymore. So if you were to do this construction here, this critical value, this torus, focus point, when you increase A, moves down and then collides with that corner. Sorry, no, it moves up, it collides with that line and creates this corner. And this lattice is global, it doesn't have monogamy. So that means also that for sufficiently large values of H, there are global action angle variables here. Right? So there's no monogamy. Okay, so then I can now formulate the main result that says that for fixed n, when n squared is larger than a, this parameter a, the joint spectrum of G and LZ has quantum monogamy. Okay, so now I'm talking about the quantum system. So let me show you what I mean by that. So I have G an operator now and LZ an operator, and they are commuting. And so I can look at their joint eigenvalue problem. So the point is, if you have commuting operators, right, they have the same basis of eigenfunctions, but they have different eigenvalues. So G and LZ, and what I'm doing is, so for each such eigenfunction that you can find, I plot LZ, and G I make a dot in my diagram, right? So that's the joint spectrum of these commuting operators. And the statement is that if you do that, well, of course, I was kind of lying when I said this is a classical picture, right? So this is, of course, the joint spectrum also, but you can think of it as visualizing the actions by Bohr-Sommerfeld quantization. But if you think of it as the joint spectrum of the quantum system, then the statement is that this system has quantum monogamy, and which means it's locally lattice, but not globally. So one of the quantum numbers is well defined, the one for LZ, but the other one is not. And because this is a topological statement about a property of the system, this is definitely different from the system when A is 0, right? So I guess they are topologically different, so there are different Liouville integrable realizations. Okay, so I guess the picture I already drew is explained one more, written out here. So if you have joint eigenfunctions, then you can look at the joint spectrum. And by Bohr-Sommerfeld quantization, which says the action is approximately a multiple of an integer plus some shift, that's the relation between the two pictures, the classical and the quantum picture. Of course, this would only give you approximately the joint spectrum, but the approximation in our case is so good that you wouldn't see the difference in the pictures. Okay, so what's the standard way to look at the hydrogen atom? Actually, well, this is when you look at H, L squared, and LZ as operators on L2, R3. And that, of course, is a very well-known problem. It leads to spherical harmonics. And the spherical harmonics, which are you can think of as the eigenvalues of these two as joint eigenfunctions. They are classified by two integers. One is the eigenvalue of this LZ, and the other one is L times L plus 1. Right? And maybe it's natural to draw them in this picture. So here's a quantum number M, here's a quantum number, this L. And if you do that, you get this triangular picture. Right? So that's the standard picture. And this is, of course, a picture that doesn't have quantum monogamy. And we're saying, instead of doing that, you can do this, right? And so coming back to my initial remarks, so here n is 12, so we have an eigenstate here, eigenspace of dimension 144. These are all the eigenstates that have energy 1 over 12 squared, minus 1 over 12 squared. There are 144 of them, and what we have done is we've chosen a different basis in that space, and we can do that for every n. Right? The standard basis is spherical harmonics, and then you get this picture. And if you choose a different basis, you get something that has monodromy when n squared is larger than a. So one thing then you can also ask yourself, well, what about these very well-known pictures, right? I mean, that you learn somewhere in school that says these are the atomic orbitals, right? So do they exist, maybe, or are we just imposing them by our choice of L squared and Lz? And in some sense, you would say, yes, they are actually a choice, right? So this is the standard choice of basis in that space. If you just have the hydrogen atom, no further perturbations or anything, then you can make other choices. And our choice is a possible choice, and it will lead to different eigenfunctions. They're not spherical harmonics. They are finite linear combination of spherical harmonics. They are called spheroidal harmonics. And somewhere here, there's a picture of them. There we go. So this is again for a particular n. 7, so here you see these 49 eigenfunctions. And up here, they look fairly much like spherical harmonics. But when you move down in the picture, you get something that is quite different from spherical harmonics. But each one of them, because we're on a compact phase space, or compact Hilbert space also, each one is a finite linear combination between that basis and that basis, right? So these are finite linear combinations of spherical harmonics. But they have the meaning as being associated to our integrable system with G and Lz. So it's a very special choice. And I guess I jumped over some pictures, some slides, which maybe I should not go back to, which tells you more about how you can do the computation and so on. I mean, this leads to Jacobi operators, tridiagonal matrices, but everything can be done explicitly and be computed. So let me maybe move on. So connection to the two-center problem, this is in fact how we kind of arrived at this by accident. We were looking at the two-center problem, actually the scattering problem and the two-center problem, and we realized, so what's the two-center problem? Two fixed centers with masses m1 and m2, and each one has its gravitational potential, and you put a test particle in that field. So it's not physical in the sense that nothing keeps these two centers from repelling or attracting each other, but they just sit fixed in space. If you have that problem, you can send one of the masses to 0, and then you end up with a Kepler problem. Right? This problem naturally is treated in spheroidal coordinates, because that's the system in which it separates. And when you do this, you end up with a version of the Kepler problem that is written in spheroidal coordinates. So spheroidal coordinates are basically elliptic coordinates rotated around an axis. So take elliptical coordinates and rotate them. So the Kepler problem separates in spheroidal coordinates. And this is, of course, also very well known. And that is the special thing about our choice of G. Right? Our G comes from separation of variables. Right? But separation of variables in a non-standard coordinate system that you may want to think of as coming from the two-center problem. So these action variables obtained from this are different action variables. Right? I mean, so each of these...
What does it mean in the A that you had a parameter A? Does it mean something in this way?
Yes, exactly. So that's the distance of the foci of the ellipses. Exactly. So that's why you go back to the spherical situation when A goes to 0 and when A goes to infinity, you end up with parabolic coordinates, basically. Right? So two special cases in the limits. So now then it becomes kind of sensible to ask this question, how many different sets of action variables are there for the Kepler problem? And what I mean by that is, well, I need to talk about toric systems, so to make that precise. And so there is a big theorem that says if you have a Hamiltonian n-torus action on a compact symplectic manifold, then the image, the momentum map, is a convex polytope. I already pointed out that when A goes to infinity, you saw this picture which was basically converging towards a rotated square. And that's would be an illustration of this theorem. So if you go to the parabolic coordinate limit, then this is, you have a t-torus, 2-torus action, and then this theorem holds and tells you that this is a convex polytope. So if the action is effective, then you get a bit more. This is, the polygon is then called a Del-Zant polytope, and this actually classifies the action and the manifold. So toric systems on S2 cross S2 have been classified in this setting by Carchon, and the image of this map for integrable toric systems on S2 cross S2 can only be one of two convex polytopes. Because it's Del-Zant, they're rigid, they can't move, much. There's a very strict condition on the slopes of the edges. And so in that sense, one can say there are two different sets of action angle variables for the Kepler problem. Okay, so these toric systems are very special. The system that I talked about, when A is a typical A, and in particular when you have a focus-focus point, they're called semi-toric systems. And for semi-toric systems, again, you would like to classify them and classify their foliation in this sense that you have F, the momentum map for one of the systems, F for the other system, and you're looking for two functions, psi and phi, so that this holds. Right? So one of them is a symplectic map, and the other one is a reparametrization of or mapping between your integrals. And so that's the notion of equivalence, and then you ask, can you classify systems with this notion of equivalence? And so this classification has been done by Pelayo and Wunok, and we also looked at this for the Kepler system that I just described, and it can be done and written out. And so each focus point has a symplectic invariant, which is not just like an eigenvalue, but it's a nonlinear invariant. It's infinitely many coefficients of a Taylor series of a smooth function, and we computed that function also in this case. Okay, but so that's just a little aside, I guess, towards classification of semi-toric systems. Let me make another remark here about regularization. Of course, the Kepler problem is singular, or it has a singular potential. And should we maybe regularize first and then see if anything changes in what I said? And there are at least two classical ways to regularize. One is due to Moser, and the other one is the Kustenheimer-Stiefel regularization. So what Moser does maps the system to a geodesic flow on S3. And the geodesic flow on S3 is clearly SO4 symmetric. It's the round sphere in S3 embedded in S4. So then you get an obvious SO4 symmetry. And then the quotient by this flow leads to a system on S2 cross S2. But the question is maybe, does it lead to the same system or is it different? Then here, Kustenheimer-Stiefel maps the system to an isotropic harmonic oscillator in R4. And so remember that I mentioned these two systems in the beginning by saying those are the standard superintegrable systems, right? So they are all connected in this way. So now you have a harmonic oscillator in R4. So if you want to go down to something with 2 degrees of freedom, you have to quotient by two flows, the flow of H and the flow of some natural constant. It's called the bilinear relation or bilinear integral, which comes from this blowing up. So if you quotient that out, you again end up on S2 cross S2, as you would expect. But the surprise, at least to me, it was surprising that these systems you end up with are exactly the same. So even though we didn't regularize in the beginning, nothing changes if we do regularize. And the reason, in some sense, may be that since we quotient by the flow of H, and the flow of H is the thing that is singular, you end up with something that is regularized, even though we didn't actually regularize. Okay, so how much time do I have? What? Yeah. Okay. So let me point to another interesting system, which is even simpler than the Kepler system, but you can do the same thing. So forget the potential in the problem. So we're just looking at the Laplacian in R3, or free particle if you want, and the quantum mechanics is the Laplace operator. So again, the Laplace operator separates in many coordinate systems, and this is well known, it has been classified, and each separation defines a set of special functions, right? So that's, if you want, that's the standard way to get special functions is by separating variables in the Laplacian, right? So now what we should do is do the quotient by the free particle dynamics. So it seems a little more complicated here because it's not compact, right? So the free dynamics is straight line motion, right? But so there are no theorems for the reduction, but of course the reduction is simple to do. So you just do the reduction, and you end up with systems on T star S2. And for each set of separation variables up here, you end up with a system on T star S2. And these integrable systems on T star S2 tell us something about the special functions of the corresponding Laplace equation. Right? And so doing the whole thing again, you find that in spheroidal harmonics, which are these special functions obtained from separating the Laplacian in spheroidal coordinates, that they have monodromy. Let me just show you. So this picture is computed by one-line command in Mathematica, right? Because Mathematica knows these eigenfunctions. Spheroidal eigenvalue is a function that computes the eigenvalues of these special functions, right? But of course, people have never looked at this joint spectrum or at global properties of the joint spectrum, right? But here you can do it now. So you just make a table of these spheroidal eigenvalues for fixed. Sorry, no, not for fixed n. So here you're letting one of these go from 1 to 20, the other one goes from minus n to n, and then you plot all these points, and you see a joint spectrum of two commuting operators that has quantum monodromy. And this is the quantum monodromy in the spheroidal dynamics. So this is work that I've done with my students Diana Nguyen and Sean Dawson. And in a way, it's a program now to repeat this for all the special functions that you obtain, right? And so this is still a somewhat simple case for spheroidal harmonics, even though it's probably not that one that a lot of people have worked with, but there are about 16 ways to separate the Laplacian. And each one leads naturally to an integrable system. And of course, these functions have been studied before. I think what we add is a kind of global description of properties of these spectra of these functions. Right? Okay, well, it's, I guess I stated a theorem, so I should say a few words at least how to prove that theorem. So how do you prove that this actually happens? So you don't actually, luckily, have to know anything about this quantum problem, because there is a general theorem due to Wu-Nok that says if the classical system has a non-degenerate focus-focus point, then all of this happens. So the only thing that you have to show is that this pinch torus that I already showed you as a picture actually exists. And that's a somehow standard, simple computation. We have to analyze the system on S2 cross S2. It has one other global S1 action, the LZ, and so we quotient by that again. And if you quotient by that S1 action, you get an orbifold but it doesn't cause any problems, and you can analyze everything explicitly and show that there is this non-degenerate focus point. So this is very similar, and I already mentioned that, to work by Cushman, Sadowski, Evstatiou, and they studied, Richard, what you asked in the beginning, perturbations of Kepler, and then the averaging of that problem. So, of course, they ended up on a system with S2 cross S2, but they actually have real dynamics on G, which came from averaging. But we don't have real dynamics on G, but we have constants of motion that come from separation. Right? And that's the object that we're studying. Right? Anyway, so if you have that, you have classical monodromy and you have quantum monodromy. And so the proof is kind of a standard thing and not very interesting. OK, so I told you about the relation between Liouville and superintegrable and in classical and quantum mechanics. And there are lots of interesting systems where this analysis can be done. And we have done a few of them already. And in particular, spheroidal coordinates lead to this quantum monodromy. If you choose other coordinate systems, you might not find monodromy. And so somehow the main point here is not monodromy, right? It's really just to say there are these interesting integrable systems related to separation of variables that tell you something about special functions. Right? I think that's maybe the main point. But it still is an interesting question, which of the coordinate systems lead to these semi-toric integrable systems? And we don't know the answer to that question. All right, I think that's all. Thank you very much.
Are there any questions?
I'll start with just stupid questions because I want more questions. So mine is the stupid one. I think the beginning of all your story is the P and Q constants of motion, right? In the Nekoroshev things. So, crazy thing. What happens if you want, instead of doing integral systems with Q and Q, take a chaotic system? Will this produce something interesting for the opposite way?
Well, I think that kind of relates to this question that Richard asked, right? So if you start with not the integrable system to start with, the Kepler problem, but let's say you start with a non-integrable perturbation of the Kepler problem. Maybe Kepler problems or two Kepler problems can be thought of as a limit of the three-body problem, right? Which is chaotic.
But the P and Q's, you can do anything with them that the Kepler problem doesn't sit.
That's right, yeah. But if you want chaotic dynamics, what I'm trying to say is then you have to start with something that is chaotic. But you can try to do this averaging over the flow of H, and that will, however, not necessarily lead to an integrable system. And then you would get a non-integrable system on S2 cross S2. Mm-hmm. So yeah, so that's possible. Of course, I mean, often what you hope is that when you do your averaging, that it leads at least to low order to an integrable system because you can analyze that better. But there is no, in general, no guarantee, of course, that by averaging you produce an integrable system. And then you would in fact get a non-integrable system that lives on this coadjoint orbit. And I think, and so the standard case is this Kepler problem across electric and magnetic fields, where people have done that. And I think to some approximation, to some order of the normal form, it is integrable, but eventually you would see this non-integrability.
So another way to split into S2 cross S2 for constant energy is you think of oriented planes in space, and that's one S2, right, by their normal vector. And then Poincaré told us how to turn ellipses onto a plane into a sphere. Mm-hmm. So that's like, so is there a simple way to see the relate? I mean, I'm sure there's formulas, but because you've split it into two S2s, and here's another one, where one of the S2s tells you what plane you're on, and then the second S2 tells you what the ellipse is on that. Am I making sense?
Yeah, so I think that's related to the description of SO4 as a product of two SO3s.
Okay.
Right? So it's SO3 cross SO3, and those are, I think, exactly the two that you just described.
Okay.
I guess one basically giving the orientation of the plane, and the other one then the ellipse in that plane.
Okay.
Okay, I have two obvious questions. I mean, very natural, obvious. There is another superintegrable system, the rigid body.
Yes, but it's not maximally superintegral.
Oh.
Right? So I guess this idea to quotient by the flow of H or something related to the flow of H wouldn't work in that case. But you're right, so in talking in terms of Nekoroshev, right, so there you have the situation that you have two i's and two phi's and a pair PQ.
Yeah.
But to do this game, you need one I.
One eye. Oh, I see.
Maybe you could put two moments of inertia equal.
Yeah, probably yes. It becomes more degenerate. Well, certainly when you make all three of them equal, then you're
When the two axes equal, it degenerates actually. Yeah, when you have two of the axes, the moments of inertia.
Yeah, but is two equal enough? I don't know. Maybe Francesco knows.
No, there is no degeneracy.
Yeah, it's only when three are equal.
No, with two moments of inertia equal and one different, there is a vibration by two-dimensional tori, just as in the general case. It does not have this, it has different singularities on the hyperbolic, on the stable. But the only real difference is that the vibration is easier to describe in
Yeah. But sorry, Christian, you had a second
Yeah,
question.
okay, and the second obvious one. So there is a Moser generalization of the Kepler problem in Rn, right? So the averaging, right? So the flow on the sphere,
Yeah,
right?
yeah.
So that one is embedding the sphere in Rn plus one. You have an SON plus
SON
one
action,
symmetry. So it's an obvious generalization.
Yeah, so that would work, I think, and then you won't end up on S2 cross S2, but on these higher dimensional generalizations, which are these Grassmannians, the two Grassmannians in n-dimensional space, which happen to be S2 cross S2 for 4 dimensions, but in general, it's, I don't know if they have some simple other description than saying that. So in terms of moduli space, I mean, that's the set of 2 planes, I guess, in Rn. But I think, yeah, so that would, yeah, I think in some, yeah, it would work. I guess what is not probably known is, actually there is a lot known. If you wanted to do something related to separation of variables so that you have a good quantum analog, I guess then you would have to think about what's the way of separating variables on the sphere. And I think that's been classified. Sorry?
What was the meaning of this? Why would one do it? Besides that, it's, you know.
Because you asked the question.
Yeah.
Francesco, I don't know, did you have another question? Or? No? You already? Okay.
I do have a
Yes.
question. So this Nekoroshev splitting of the variables, PQ, I, phi, is that canonical? I mean, is that something that the flow naturally wants to do, or are you imposing it in some way?
No, so this is the opposite to what I'm doing, right? Because I'm doing the non-match all thing, and I'm finding some eyes that are not there. But what Nekoroshev said is, I guess to start with, you should look at the dimension of your dynamical tori, right? So the actual dimension of the tori as they, let's say, an irrational torus, right, has a certain dimension for a generic initial condition, and that may be less than half the dimension of phase space. That number you have to find first, right? It may not be easy to find that number, but once you have that number, then the splitting is canonical in the sense that these action variables will be unique up to unimodular transformations again, right? But that's, of course, you can't get rid of that. Right? So, but then you have I phi, and PQ is local symplectic coordinates, so there is lots of choices for those.
One last question.
Can you explain a little more about the geodesic flow in the 2D sphere?
Yeah. So this is the geodesic flow on the round sphere. So the orbits are great circles. And when you quotient by the flow, then it means you're identifying all the great circles to points, and then you ask yourself, what is the space of all these points, right? And the answer is that's S2 cross S2. Right? And by the same argument, because a great circle is basically intersection of the planes with the sphere, so you're asking what is the set of two planes in R4, and that is S2 cross S2. That's this Grassmannian. But that, I think, is a good way to see the Grassmannian in the general way. So the geodesic flow is always great circles. That means two planes, and so if you want the orbit, all possible orbits, then you're asking for what's the set of two planes in Rn.
Okay. Question, one short comment, and then we'll move to the next speaker.
No, I just wanted to make a comment, maybe an historical one. This superintegrability point of view has been introduced in the first time by Nikoroshev, and actually it goes beyond, in a way, the description given by the Regularization theorem, by the standard complete integrability, in those cases which are superintegrable. The real geometry, the real description adapted to the dynamics is given by the superintegrable point of view, not really by the integrable. This is one comment. And maybe this has not yet been really metabolized by the community. The second comment I would like to make is that the Nikoroshev article in 1972 was really a breakthrough in a way. For instance, the notion of monogamy that we all, that is usually attributed to Dijksterman's article in 1980 is already present in the Nikoroshev article of 1972 as a complete understanding and description of the monogamy.
This is comment in at the end of Dijksterman's paper that monogamy was described by Nikoroshev 10 years ago. Yes,
in the 1980 article, there is a comment that Alan Weinstein knew the entire structure, but there is no reference to the Nikoroshev.
Yes, there is at the end of the Dijksterman's paper about results of Nikoroshev.
Okay. Thank you again.